In this video, I'll highlight some of the engineering design of this machine, the Ember Precision Desktop 3D Printer. It was manufactured and sold by Autodesk, but now discontinued. All its details, though, are open sourced, and so it might well live on. There are many ways to perform 3D printing, but they all have in common this. They take a 3D model, cut it into many thin two-dimensional slices, and then they print these slices one at a time, one on top of the other, to create a three-dimensional object. 3D printing promises a revolution in manufacturing. One company that uses 3D printing to manufacture turbine blades reports that it reduces pollution, takes a quarter of the time to develop a new blade, partly because of rapid prototyping with 3D printing, and that they can repair the blades 60% faster. Futurists have imagined mobile production plants rapidly deployed to disaster zones. They can print arm splints, tent stakes, and even buildings. One company has pioneered 3D printing of concrete buildings. While this promise is enormous, today I'm not creating anything exotic, but focusing on printing this. Odile the Swan. It's one of several items used to test and benchmark 3D printers. On this printer, the Swan is created here on the lower side of what is called the build head or build platform. Odile will be printed upside down here, like this. The printer will first build the base and then work its way to the Swan's head. Let's watch the printer in action. The print head descends into this amber tray, which contains a liquid called resin, which will solidify. There you can see the print head settle into the resin. And let's watch the action right here on the print head. Here's a close-up. The printer exposes the first layer, that's the flash of light. Then the tray slides sideways, and then returns so another layer can be added. You can't see anything yet, but I'll speed everything up, and then there. You see in about 35 to 40 minutes the base of the Swan appearing. Remember, it's printing upside down. And by about an hour, the Swan is done. Let's examine the key steps used to print this Swan. Specifically, I'll look at how that flash of light creates a solid layer, why the machine's build head moves upward, and then explain why the tray moves sideways. And that will take us through the essentials of the machine's design. After that, I'll look at a few details of the chemistry of the resin. Let's start with that flash of light. The flash creates a solid layer. Here's how. The tray is filled with liquid resin. It solidifies when exposed to blue light, which appears green when photographed through the orange tray. That orange tray shields the resin from room light, which might solidify the resin inadvertently. To show you how this works, I filled this watch glass with a bit of resin. I printed the Swan with clear resin, but here I've mixed in some black resin to show solidification better. Watch what happens when I shine this blue laser on it. Almost instantly, the resin solidifies. It's called curing. What I'm doing with this laser pointer is pretty crude, so to aim light precisely, this printer uses a DLP projector. DLP stands for Digital Light Processing. The tray has a clear window, so light flashes can cure a layer. This is the base from a printer we took apart, so I can show you what's inside. Sitting on the base is the amber tray that contains the resin. Note that the silicone-coated window of the tray is positioned over a window in the base, and inside, there's a bundle of electronics that contains a powerful LED, a light-emitting diode. It produces blue light of a narrow range of wavelengths. Then some optics spread that beam of light and shine it onto a device called a micromirror that creates the light pattern appropriate for a particular layer. Then a mirror reflects the layer pattern through the window in the tray and onto the resin. Micromirrors were developed by Texas Instruments for use in projectors for computers. This is the optical train of the printer. You can see the micromirror if I take off this lens and look down the barrel. It's a small chip, about 3/4 of an inch by 1/4 of an inch. It's comprised of a bit over 1 million tiny mirrors, each about 8 microns by 8 microns square. Recall that a human hair is some 80 microns. A micron is a thousandth of a millimeter. This drawing shows 2 of the mirrors. Each of the mirrors can be controlled separately. An electrostatic force generated by small voltage pivots a mirror plus or minus 12 degrees. This directs reflected light either onto or away from the resin. Because these mirrors are so tiny, light can be directed to 50-micron sections of the layer, so the printer has a high resolution in the XY plane. Underneath the mirrors is a slender post. It's a mere 1 micron or so, and below that, an elaborate yet tiny hinge. It would seem that such an assembly would be fragile. You picture a million mirrors clattering back and forth as this machine is moved, yet that's not true. The mirrors are so small that they don't respond to the vibrations and shakes from normal handling. Nor does their pivot wear out easily. Tests show that the mirrors could flop back and forth for 11 years of continuous operation before the pivot fails. To see the layer images created by this micromirror, I'll put a yellow card right here where the layers are created. Remember that what we are looking at here are the layers of the swan which are printed one by one on top of each other. As we watch the layers, keep in mind the printed swan. Here, the thin red line in the yellow block on the swan indicates the cross-section being printed. In the projected images, the bright blue areas are where light is reflected on the resin and cures it. The dark areas reflect no light on the resin, and so it stays liquid. Notice the round circles. These are the support posts created when the swan prints. They're more easily seen here when highlighted in blue. These are later snapped off the swan. Let's speed up the printing and watch the swan being formed. All the tiny circles coming up are the support posts at the very bottom. Here, the base prints. And then the body. You can see the wings begin to take shape. These are the top of the wings. The round blue dot on the right is the swan's neck. And then the blue flashes disappear as we reach the top of the swan. Now, let's turn to why the printer's build head moves up rather than down. It's called bottom-up printing. This dramatically reduces the amount of resin needed to print the swan. When using light to cure resin, there are two main ways of doing this. The bottom-up, used here, and top-down printing. In top-down, a platform moves down into a vat of resin while light is projected down from the top. The great advantage of this top-down is that it is easy to expose a layer to light and cure it, but it also has a very big drawback. The vat must be as tall as the part to be printed. And this requires a large volume of resin, which can be very expensive, particularly if the resin has a finite lifetime. In contrast, the bottom-up method uses a shallow tray that requires a much smaller amount of resin, even for tall parts. I find it stunning to watch a large object being drawn out. Next, let's look at why the resin tray slides sideways after each layer. In a bottom-up print, the layer is built on a window. This machine would fail if the cured resin stuck to the window. Most 3D printing resins have the property that oxygen hinders the chemical reactions that cause them to solidify. To allow oxygen into the layer, this window is made from silicone, a material highly permeable to gas. Oxygen residing in the window diffuses into a thin layer of resin just above the window. This layer is 5 to 50 microns thick, but the concentration of oxygen in this layer is enough to prevent the resin curing directly on the window. Yet even with this silicone window, the newest layer will still partly adhere to the window. If it does, then no fresh, uncured resin will be able to be added, and so no new layers. So the newest layer must be separated from the window. There are several ways to do this. Some printers just pull the layer up, yet this direct pull, as it's called, can create problems. This layer is like a suction cup. Now, you can see that by putting a cup in a puddle of liquid on a plate. As I lift the glass, I can feel some resistance. You can even hear when it separates. And so in a 3D printer, to separate layer and window requires a large motor to lift the printhead. This action might damage the layer. I find it easy, though, to slide the glass to the side, raising it slightly as it follows the contour of the plate. In general, the force from pulling up scales as the fourth power of the radius of this opening, while sliding scales as the square of that radius. So typically, sliding requires 1/100th the force of pulling up. And for this reason, this printer slides the tray to separate layer and printhead. Other printers peel the layer off with a rocking motion. The key takeaway here is that printing parts with large cross-sectional areas is very difficult. This lattice has a fine, detailed structure and looks impressive, but because it's mostly open space, it's actually one of the easier types of objects to 3D print. That's why demos from 3D printers rarely show a thick, brick-sized object like this. The forces are much greater, print speeds are slower, and it's impossible to print for many stereolithographic 3D printers. We've been looking at the mechanics of how the printer works, but this printer relies on both mechanics and chemistry. The combination of precise motion, micromirror, and fine-tuned chemistry creates the resolution of this printer. The resin contains 3 main ingredients. First, there are 2 types of molecules that will together form the rigid network. These molecules come in 2 sizes, a monomer and an oligomer. The latter is just 3 or 4 monomers bonded together. Second, a photoinitiator that when struck by blue or UV light starts a chemical reaction that links together the monomers and oligomers. This solidifies the liquid resin. It is the balance of the monomer and oligomer that yields a piece that is rigid and well printed. For example, here's a tiny boat, it's often called Benchy, that we printed using only monomer, no oligomer. If I squeeze it, you see it's no longer rigid, and in fact, it'll even break. And equally dramatic is leaving out the third chemical, a UV blocker. This chemical prevents the blue light from penetrating too much past the layer being printed. Here, the boat is printed with a UV blocker. You can see the resolved details in the boat. Keep your eye on the circular hole in the middle. Here is the same boat printed without UV blocker. Compare the hole here and here. Without the UV blocker, the light cures regions of the boat that were meant to stay liquid and lowers the resolution significantly. There's, of course, much more to be said about an engineered object like this, so I've linked to other videos that might interest you, including several that describe the micromirror in detail. I'm Bill Hammack, the Engineer Guy.